we will be discussing an important book. While most books on artificial intelligence in the field of social sciences are dystopian, we will be looking at a book by an author with a positive outlook. Ray Kurzweil's book.
Yes, that much debated book with the title Singularity is near.
This book addresses it as a historical shift. We're talking about the technological singularity. Our mission today is really to get into the blueprint for this future, a future that might not be defined by biology as we know it, but by accelerating non-biological intelligence.
It's important looking at the source material to understand the singularity isn't just, faster phones or computers. It's defined as that specific point, that era when non-biological intelligence merges with our biological intelligence and then rapidly, vastly exceeds it.
It passes it.
Utterly surpasses it. And the promise there, the kind of mission statement woven through the source text, is solving those really ancient human problems, disease, poverty, even aging itself.
Okay, so before we even get to reversing aging, we need to understand the engine driving all this. The sources call it the law of accelerating returns. LAR. The core idea is, I understand it, is that progress itself is speeding up. Not just steady progress, but the rate of progress is growing exponentially.
Exactly. That's the meta idea. The pattern underneath the pattern and the data points they pull out are frankly stunning, especially in computing.
Give us an example.
Okay, think back to, say, the late 1960s. MIT had this huge multi-million-dollar mainframe. Its processing power was about 0.25 MIPS. Millions of instructions per second quarter of a Mephius. Now jump forward to 2004. A pretty standard personal computer, maybe costing $2,000, could deliver around 2,000 Mephius. Wow.
Okay, wait. From 25 MIPS in a giant expensive machine to 2,000 MIPS in a desktop box?
That's right. The cost per MIPS, the price performance, it changed by a factor of about 8 million to 18 million in roughly 4 decades. And it keeps going. The capacity of information tech. Think cost per transistor cycle it's been having about every 1.1 years.
That's faster than the old Moore's law.
It is because this law of accelerating returns isn't tied to one specific technology like silicon chips. It jumps when one technology hits its limits. Its curve starts to flatten
like vacuum tubes.
Exactly. Before vacuum tubes even peaked, transistors were taking over, then integrated circuits. The exponential trend continues by leaping to the next paradigm. It just keeps finding a way.
And you feel this, don't you? This constant acceleration. It's reflected in how fast new things take over society.
Yeah, the paradigm shift rate itself is doubling.
Right? The sources mentioned the radio took, 31 years to reach mass adoption in the US? But the World Wide Web only 7 years?
7 years. That relentless shortening of adoption cycles, that's the LAR in action. And it's the fuel for everything else we need to talk about.
Okay, so if LOR is the fuel, what are the engines? The sources point to 3 specific revolutions, right? GNR.
That's it. Genetics, nanotechnology, and robotics /AI. They're overlapping, feeding into each other. And they're where this information revolution gets applied to fundamentally change us and our world.
Let's start with genetics. I was really struck by something the sources said about our actual genetic code.
Yeah.
Surprisingly small.
It is, isn't it? It really reframes biology. You think of the genome as this vast, complex library, but once you compress it, get rid of the redundancies.
Like zipping a file.
Kind of. Yeah. The essential information in the entire human genome is maybe only 30 to 100 million bytes.
That's smaller than a lot of software apps on my phone.
Exactly. So it suggests biology is fundamentally an information problem. We're not dealing something infinitely complex, perhaps, but more like what? Like software that has some bugs, some obsolete code.
Obsolete genetic programs, the sources call them, which leads to aging.
Right? And the mission in the genetics part of GNR is essentially debugging that software. reversing aging by tackling the known root causes like DNA mutations, toxic cells, building up telomeres, shortening the 7 key processes.
And one of the really wild ideas mentioned is something called therapeutic cloning via transdifferentiation. That sounds intense.
It does. Yeah, so it's unpack transdifferentiation. It's a pretty advanced concept. It means taking one type of fully specialized adult cell, maybe an easily accessible skin cell, and reprogramming it, turning it into a completely different type of specialized cell.
So, skin cell becomes a liver cell or a heart cell.
Precisely. Or pancreas cells, whatever's needed. And the key things are these new cells have your own DNA, so no rejection issues,
Right?
and crucially, they're generated with fully extended youthful telomeres. It's like getting brand new factory fresh replacement parts made from your own biological material. Regeneration on demand.
Okay, that's mind-bending. Which brings us logically to nanotechnology, moving from information and biology to actually building things atom by atom.
Exactly. Mastery over matter at the molecular scale. The sources were predicting that by the 2020, so around now really, we'd be building complex mechanical and electronic structures with feature sizes under 100 nanometers.
And this is the domain of MNT, molecular nanotechnology.
That's the turn, yes. MNT is about using these nanoscale capabilities to build complex systems potentially far beyond what silicon allows. Think 3-dimensional circuits built from carbon nanotubes.
What kind of performance are we talking about there? Is it just incrementally bad?
No, far from it. The projections are astronomical. A single cubic inch of mature nanotube circuitry, potentially 100 million times more powerful than the human brain.
100 million in a cubic inch.
Yeah, the density and power are almost unimaginable. And MNT is what enables the next leap in biological intervention. Nanobots, tiny robots in your bloodstream.
Okay, nanobots. What's their job description?
Think of them as the ultimate internal maintenance crew. Microscopic surgeons and cleaners.
Doing what exactly?
Their proposed missions are pretty comprehensive. Patrol your bloodstream, remove toxins and debris, identifying correct DNA errors in cells before they cause problems. Pair damaged cell membranes. Reverse atherosclerosis by clearing out plaque, essentially performing constant biological repair and upkeep.
So potentially stopping aging altogether?
Or reversing it indefinitely. That's the implication in the source material, yes. Indefinite reversal of aging through continuous molecular repair.
Wow. Okay, G on AM. That leaves our robotics and AI reverse engineering the mind.
Right? And we need to distinguish here. We already live surrounded by narrow AI, don't we?
Sure. Fraud detection, logistics, translation, even military drones like the Predator AI specialized for one task.
Exactly. But the singularity hinges on strong AI, artificial general intelligence, that matches and then exceeds human capabilities across the board. And the benchmark for that is the human brain itself.
How much computing power does that take?
The estimates vary a bit, but the sources put the figure for functionally emulating the whole human brain somewhere between 10 to the 14th and 10 to the 16th calculations per second. That's 100 trillion to 10 quadrillion crepes.
That sounds like a lot. Where are we with that?
Well, it is a lot, but supercomputers have been making huge strides. Machines like IBM's Blue Janelle were already hitting the lower end of that range years ago. So the sheer hardware power is becoming feasible.
But raw power isn't enough, is it? You need the software. You need to know how the brain actually works.
Precisely. Hardware gets you the processing power, but you need the algorithms, the architecture. And that's where reverse engineering the brain comes in, and we're seeing real progress there.
Like what?
The sources highlighted some fascinating work on specific brain regions. For example, modeling the human auditory processing system.
Okay,
They developed models based on how we think the brain processes sound. And these models could actually replicate the cocktail party effect.
the ability to focus on one conversation in a noisy room.
Exactly that, picking out one voice amidst all the background chatter. The fact that we can build systems that mimic that complex filtering suggests we are genuinely starting to crack the code to understand the brain's underlying algorithms.
So putting it all together, we've got this accelerating technological progress, the LAR, we've got the tools developing GN and R, and we're starting to understand the software of the mind. What happens when these forces collide? The sources paint a picture of, well, fundamentally changing what it means to be human, blurring reality itself.
That's a good way to put it. The lines blur significantly. Take virtual reality. The sources laid out a timeline early 2010 for convincing visual auditory immersion, maybe through eyeglasses.
Right? Like advanced AR/VR headsets.
Then, by the late 2020s, the projection was for full sensory virtual reality. Smell, touch, taste, the works. Completely indistinguishable from physical reality. Potentially piped directly into our nervous system via those nanobots we talked about.
If VR becomes that good, what happens to the real world?
Well, the implication in the text is pretty radical. Things like physical offices might become obsolete. One quote was, "Real estate will become virtual." Your location matters less than the richness of your simulated or augmented experience.
And this leads to the ultimate step, right? Transcending biology altogether that's projected for the 2040s.
Yes, that's where the molecular nanotechnology, the MNT, really comes into play for us, not just for building computers. This is the idea of version 3.0 bodies,
Version 3.0.
enabled by advanced MNT manufacturing. Humans could potentially modify their physical forms rapidly or even switch between different platforms. You might have a biological body one day, a non-biological substrate the next, or some hybrid.
So, our consciousness, it becomes software, a pattern of information that can be run on different hardware.
That's the core concept. Your identity isn't tied to the specific atoms of your body anymore, but to the pattern those atoms represent. A pattern that can theoretically be copied, backed up, moved.
Okay, that level of power, it's exhilarating, but it must come with absolutely terrifying risks. If MNT can build reality atom by atom, it could presumably unbuild it too.
The sources are extremely clear about the dangers. They call them grave dangers, and they don't mince words. The most visceral, perhaps, is the gray goo scenario.
Uncontrolled nanobot replication.
Exactly. Imagine nanobots designed to build things using carbon atoms, which is basically all life on Earth. If they were programmed or accidentally malfunctioned to just replicate themselves without limit,
They'd consume everything. The entire biosphere.
and the speed is what's truly chilling. The sources actually calculate it without specific pre-planned defenses like counter nanobots, sometimes called blue goo. They estimate the complete destruction of Earth's biomass,
How long?
approximately 3.5 hours.
3.5 hours to destroy all life.
That's the calculation. It highlights that in this kind of exponential technology scenario, there's no room for error. There's no gradual decline you can react to. Failure is catastrophic and almost instantaneous.
That just changes everything about risk assessment. What about the AI risk, the strong AI we talked about earlier?
That's perhaps the more subtle but equally profound existential risk. Once you create an intelligence vastly superior to your own, how do you ensure it remains aligned with human values? How do you control something that thinks millions of times faster and better than you?
Can you?
The sources argue that it's currently impossible, maybe fundamentally impossible, to design foolproof containment or control strategies. How can you guarantee friendly AI when its intelligence operates on principles we might not even be able to comprehend? Intelligence itself, once it reaches that level, might be inherently uncontrollable.
So the defenses, the blue goo, the AI safety measures, they had to accelerate just as fast as the threats themselves.
Precisely. It creates an incredibly high-stakes race. Defensive technologies must keep pace with offensive capabilities, and this puts immense pressure on our ability to adapt.
How so?
Well, think about regulation, especially in areas like biotechnology or AI safety research. If our current regulatory systems designed for slower technological change significantly delay the development and deployment of crucial defensive technologies, we could lose the race simply because we were too slow to react. The framework itself becomes a vulnerability.
It's such a profound, almost species-level transformation we're discussing. By the 2040s, the sources suggest the non-biological part of our intelligence, this kind of enhanced cyborg mind, will exponentially outweigh the biological part, resulting in a civilization that's, well, very different, continuing that evolutionary impulse towards greater complexity and knowledge, but in a radically new form.
It really pushes you towards some deep philosophical questions, doesn't it? And the sources touch on this right at the end. If our identity or consciousness becomes this pattern of information, what's the actual lifespan of information itself?
What do they conclude?
That information, whether it's your personal memories or the sum total of human knowledge in a library or database, doesn't just last forever on its own. It only survives as long as someone actively cares about it.
Cares about it?
Yeah, it needs constant maintenance. Think about old file formats, decaying storage media. Information needs to be actively curated, migrated to new standards, backed up, valued. Otherwise, it degrades. It becomes inaccessible. It effectively ceases to exist.
So this future of potential immortality.
Yeah, it isn't automatic. It's not guaranteed just because the tech exists. It seems not. It's more like a continuous, active process. If your very being is software, and software needs constant upkeep and upgrades to remain compatible and functional, then your survival, your continued existence, might depend entirely on the ongoing collective will of civilization to preserve and update that pattern.
It makes survival sound conditional dependent. It does, which leads to a final, maybe unsettling thought to leave you with. If your identity is just a pattern, and that pattern needs constant tending by others to survive, does that mean your ultimate existence hinges entirely on future generations wanting to keep you around, on their decision to maintain your pattern? What happens if they decide not to?